So this is the first lecture for Chapter 1 in ECE 343 Signals and Systems. Before we get too much into the material, I'd like to just do a brief overview of the main goal of this class. If we can understand this basic block diagram, we really will have accomplished the majority or a major component of what this class is all about. This diagram depicts a very common engineering situation where you have some form of input signal feeding into a system. That system operates or acts on that input signal to generate an output. We definitely need to handle these kinds of representations as engineers, and we need to do so mathematically so that we can be precise in the way that we understand and design systems to carry out desired behaviors. In this particular case, I'm going to do some introductory notation. Our idea of an input signal, for this class, we're going to use the letter X almost always to designate our input. And that input, X, usually has a independent variable, which most of the time in this class we're going to take to be time. So I'm going to go ahead and show this as x of t. This is a function x, a signal, that is a function of the independent variable time. You could think of this as my voice, for example. So my voice is a pressure wave going through the air, right, that is varying with time. As my vocal cords move around the air that my lungs are expelling, I'm creating this pressure wave, which hopefully conveys some information to you during this lecture. So my signal here might be my voice, x, as a function of time. That goes into some form of system. Lots of systems can interact with these input signals, and out comes then some generated output signal. I might put my voice through a filter of some sort, for example, cut out some of the high frequency or cut out some of the low frequency, maybe do some clipping on there. Lots of different ways that we can modify an input signal to generate the output signal. We'll go ahead and call the output of this system as a variable y, also as a function of time. So input signal x into some system generates an output y. We'll find out later that there's lots of ways of describing systems, but for much of what we do in this class, we're going to use letters H, either a lowercase or an uppercase, to designate something about that system. This is just the beginnings of our mathematical depiction for signal systems and their interaction. So I have a signal x of t feeding into a system H to generate an output y. If I wanted to start a mathematical description of this whole operation, then I might say something like this. I might say y, the signal, right, the output, is equal to the system H operating on the input x of t. And it's going to be our job or our goal in this class to be able to mathematically describe signals x and y, to be able to mathematically describe systems H, and then to also mathematically describe the interaction between signals and systems to generate new outputs, something along those lines. So that's where we're going to be going for the majority of the class. To provide just a little bit of an example of a system, here I've got one that's operating on an image. This particular image has an image that is comprised of two different colors, dark blue and light blue. They're all mixed together, and if you just focus on that left image, it might not seem too meaningful. I'm going to run that through a color filter. This particular color filter blocks the really dark blue and lets the light blue pass. So it's a form of color filter. It passes light blues and it blocks dark blues. And what comes out on the right-hand side then is just all the light blues getting rid of all the dark blues. And certainly that particular image is a lot easier for our brains to process and recognize. All that dark blue turned out to be some sort of meaningless noise, if you will, and the underlying letters, the underlying message was that light blue. This is a typical kind of example of what a filter or what a system would be doing to an input. You have some input, maybe it's noisy. We want to apply some sort of system operation, help get rid of that noise, clean things up so that we can get a better or cleaner copy of the signal of interest. So let's go ahead and dive into Chapter 1. There's a lot in Chapter 1, and it starts with the taking a look at signals. We need to be able to understand the signal before we can talk about the system, and we certainly need to talk about both signals and systems before we can talk about their interaction. The logical place here to start is a signal. So really, what is a signal? A signal, right? A signal is just a function. It's a function of one or more. Could be more. For this class, we're going to deal mostly with one. It's a function of one variable or variables, more variable, right, that conveys information. That conveys information. Almost everything of interest to us as humans can be somehow cast as a signal. So we already talked about this idea of a signal x of t, which we'll take as an input in this class. You might have another signal y of t, which we take as being the output of a system as an example. That's pretty generic so far. The class of all signals is probably too broad to be fully useful. So we're going to work on kind of whittling this down, breaking it apart. It's what engineers, we divide and conquer when it comes to understanding things. And so we're going to try to break this study of signals up into multiple pieces. If we can learn some different classification signals and some different properties of signals, it will greatly simplify our ability to competently work with signals. I'm going to just follow book order in the following presentations. It's a little hard at this point just because we're starting from scratch, and it's a little awkward to do that because you don't really have the introduction of everything. So you got to start somewhere. What I'm going to start with is just talking about one way of classifying signals. We can classify signals based on their size. So let's look at signal classification. Signal classification. Signal classification, and here we're going to talk about the size of a signal, and we're going to measure that size of a signal through a concept of either energy or power. We use energy or power here in this class in a little different way than you probably saw back in circuits or other electrical engineering class. These are unitless quantities that are more of an abstraction, if you will, but we can relate it to the idea of circuits. So if I had a voltage, for example, and I hook that voltage source up through some sort of resistor, right, I know that there would be some current that could go through there, I, and we could think of something like power is equal to the current times the voltage. We know that with a resistive load like this, that the current is equal to voltage over resistance, or I could say that the voltage equals current times resistance. So I could rewrite this IV as being equal to a V squared by R, or I could write it out by as an I squared R. What we'll notice in all of these cases is that this idea of power is connected to something squared. So we think of power, right? Power as being related to something squared. And for us, when we also talk about signals, it's not just going to be something squared, but it's going to be something squared taken over all values of the independent variable. So it's like an average squared value is what we're going to look like. So let's go ahead and take a look at this. We're going to look at two measures of signal size, and what we're going to find is that they're mutually exclusive. If you have one, you can't be the other. This classification is just really handy because if we know a signal is of one class, then we know it's not of another class as long as those classes are mutually exclusive. And that helps us maybe direct us to some appropriate mathematics to deal with the signal of interest. So let's talk energy signals. So in this class, when we talk about energy signals or the energy of a signal, we're just going to talk E sub x. That's going to be read as the energy of x. And it's going to be, let's do it as a limit as some parameter t goes off to infinity. And I'm going to do an integral minus t by 2 to t by 2. So basically, I'm going to be looking over an infinite line of the signal's value squared dt. This is the way the book does it. I can tell you right now, I'm not a super big fan of this notation. My preference is to be just a little bit more mathematically precise in this, and that would be to do this not as a signal squared, but to do it as a signal's magnitude squared. So for me, I would prefer to put in x of t quantity, that magnitude squared. This is just a little more general. It works for a broader class of signals, and it's really what the vast majority of times engineers mean by the energy of a signal. The other definition is fine if the signal is real, but it would not handle a complex signal appropriately. So I would just encourage you to go ahead and make that substitution. You'll not notice it most of the time because most of the time we're dealing with real signals, but let's go ahead and do it the right way and do it as the magnitude of a signal squared integrated over all time. So energy is really what? You square the signal and then you just integrate, add up, if you will, all that squared content. You could probably guess that there's going to be certainly cases where this turns out to be a nice number, some finite number, okay? And you could probably also guess cases like a DC signal. If a signal was DC, a value of 1, for example, everywhere, 1 squared is 1. And if you take 1 and integrate it from minus infinity to infinity, that blows up to infinity. So there are signals that would have difficulty. They would have infinite energy. So when we talk energy signals, something along these lines, we're going to say x of t is an energy signal. It is an energy signal, right? It is an energy signal if that energy of x is a finite number, okay? I might make the comment that periodic signals, something like a sinusoid, periodic signals can't be energy signals, right? Because they go on forever and they'd have infinite squared content. So it takes a signal that could be quite complex. It could be varying in lots of different ways and replaces it with a single number. And that number, that single number that energy reflects, tends to get bigger as the signal gets bigger. So it is a measure of size. There is another form of size, and we're going to look at that and call it power. It's related to energy in a way. It's just a normalized energy, if you will. I'm going to again remind you that these are not the unit the unit values that you might have seen back in a circuits or an electronics class where they talked about power and energy and they put some unit on there like watts or joules or whatever the case may be. So these are just unitless quantities that are indicative of size of a signal. So power of x we're going to do is being equal to, it's still going to be a limit, right? It's still going to be a limit as t goes off to infinity, something along those lines. We're going to still have an integral minus t by 2 to t by 2, something along those lines. We are still going to have that magnitude x of t quantity squared. Book would not put the magnitude on there. We will do it this way just because it works for a broader category of signals. The only difference now is that we're going to put a 1 by t in there. We're going to be normalizing by the amount of time that we're looking over, and it turns out we're looking over everything. So it's an average energy, if you will. It's an average energy, something along those lines. If I take a look at a periodic signal, so something that repeats, for periodic signals, those that repeat, right? With some period, and let's call that period t, okay? Power can be computed in that case as the following. We can look at it as p of x being 1 over t, just integrate over a single period of that signal squared dt. How is this different? It shows that we're not going over all the time, right? So this first one, we had a limit as t went off to infinity, and we went and integrated over that full minus infinity to infinity then. Here, we're just doing it over a single period. How does this work? Well, one of the ways that we might think about it is by taking a quick look at an example. So I'm going to just do this in a sort of a graphical way to help demonstrate this. Let's go ahead and take a look at a signal that looks something like this. It's just going to be this nice little sawtooth waveform, something along these lines. So this sawtooth waveform is just going to sit there and be repeating forever, same sort of thing. It goes on forever, periodic waveform, something along those lines. I'm going to let it have a peak height of 1. That means over this first interval, let's let this first interval go 0 to 1, so this thing has a period of 1. It would be parameterized as t, something along those lines. And I'm going to call this whole signal x of t, something along those lines. If we thought about what the power of x looks like, that is a limit, right? Limit as t goes off to infinity, 1 by t, integrate over a t interval window, right, of the size of x of t squared dt. Let's think a little bit about that inside. We're taking x squared, something along those lines. So if I looked at that in my graph, I would get something that would look like this. It would be this quadratic kind of form, repeating over and over and over again. So I get a t squared there in that first part, something like that, right? And that just is repeated. So this is my magnitude x of t squared, something like that. And now I just need to be able to find the area of this guy, right? Need to be able to find the area of this guy divided by the amount of time that the signal persists, in this case going on from minus infinity to infinity. Find all the area there and then divide by that total width. First off, we might think about what's the energy. There is an area of this signal over a finite interval, and then that repeats forever. So let's look over this first interval, and I'm going to just color it in dark red here, 0 to 1, right? If I wanted to think about the amount of squared content there, if I did an integral 0 to 1 of my t squared dt, what do I get? I get a t cubed by 3 going on the interval 0 to 1, that's 1/3. So the area, right, the area of that kind of dark thing, right, is equal to 1/3, something along those lines. So if I wanted to know something about the energy of this guy, energy of X, right, I'm going to get a third plus a third plus a third plus, and keep doing that forever, because there's an infinite number of these little pieces, each with area a third, and that heads off to infinity. So this is not an energy signal. We'd already mentioned that before. Periodic signals can't be energy signals because it has not finite energy, but it has infinite energy. We could be interested in the power. I could try to do power through that limit, going over all minus infinity to infinity, something like that. But that might get a little awkward. I'm going to do it instead in a kind of a little bit more clever way. I'm going to do it over that period, but I'd like to show that it's the same thing. So let's think about what this equation is doing, but let's just build it up slowly. Okay, so let's build this guy up slowly. Let's start first by looking at what this thing looks like, right? Going from -1 to 1, right? Something along those lines. So an integral -1 to 1 of that signal, right? X of t quantity squared dt. So I'm going to be integrating here not over all infinite time, but over a window of width 2. So because I'm doing it over a window of width 2, I'm not going over infinite time, I'm just going over 2, and those integral limits reflect that, so I need a 1/2 out front, something like that. So this is not done, it's just getting a start on that. Well, we already know what the integral of x of t squared is over 0 to 1. That was a third. There's 2 of those guys, so that's going to be 2/3. So I know in this case I'm going to get a 1/2 times 2 of those 1/3 pieces. And guess what? Those 2's cancel. If I go out and double the amount of space I'm looking over, so instead of doing 2, I do 4. So I'm going -2 to 2. What would that look like? That would be 1/4, because I'm taking 4 of those little pieces, going over that width of 4, so -2 to 2 of integral x of t squared dt. And I'm going to get 1/4, and then there's 4 of those pieces, that is each of 1/3. The 4's cancel, and I'm still left with a 1/3, right? And it wouldn't matter how many I do. If I went back and did this again, and I had all these pieces in there, and I looked in there and there were n pieces, right? There are n pieces. I'd get 1/n, all right, because each was 1 unit in length, so 1/n is the total width, and then there's going to be n of these 1/3 areas in there. The n's always cancel, and I just get that 1/3, which is the 1 period integrate over the period of my signal squared, something along those lines. So that does give a bit of a graphical approach to justifying this idea for periodic signals anyway, right? That I end up getting something that turns out being more easily computed just by looking over a period. So just continuing in the last little details of this, if px, right, has values between 0 and infinity, then x of t is a power signal, something like that, okay? So if, as a final bit of stuff, 0 is less than e is less than infinity, right? What does this imply? That implies that the signal is an energy signal. That means that its sum of squared content is a finite number. Energy, right, is then divided by infinity to give us power. If you have a finite number divided by infinity, that implies that this power, right, has to be equal to 0. So if I have an energy signal, its power is necessarily 0. If, on the other hand, right, 0 is less than p is less than infinity. That means I have a finite power signal. That really implies that the energy of the signal must have been infinity, because the only way you can get a finite number, right, the only way you can get a finite power when that power is computed by energy divided by infinity is if the energy itself is infinity, something along those lines. And we will note that power and energy are mutually exclusive, right? So if you are energy, you can't be power. If you're power, you can't be energy, something along those lines. So this is just our baby steps of trying to get into some sort of understanding or way of describing signals. We started out with a really basic one of energy and power signals. Why might we use something like this? Well, it turns out that if you have an energy signal, some types of math are more appropriate than if you had a power signal. When we later get to, for example, Fourier analysis, power signals require a different flavor of Fourier than do energy signals, as an example. So these signal classifications and signal descriptions just help us get a better understanding of signal, and they'll point us to the right mathematics. Okay, we're going to switch gears again. This is all going to be under basic signal operations. So let's look at basic signal operations. We know what a signal is. We found one way of classifying signals according to their size, energy, and power, and now we're going to talk some basic signal operations. There is a set of operations, and so let's talk about operations on what is called the dependent variable. I'm not going to spend a lot of time with this because these are operations that I'm pretty sure that almost everybody in the class should be very comfortable with. So if I have a signal x of t, right, the dependent variable is the x. So we're going to be talking operations on that dependent variable. For example, we could talk about an amplitude scale kind of operation. What would that look like? That would look something like this. I take some scale factor c and I multiply it by x of t, right? What does that do? Mathematically, it says take every amplitude that x has for all the different values of time, and for each one of those amplitudes, multiplying each point by point, element by element, if you will, by some value c. If x of t, as an example, right, was just a DC value of 1 for all time, and I let c be equal to 2, then 2x of t, no surprise here, right, is just going to be a value of 2 for all time. Everybody has done this sort of stuff. You've taken signals and multiplied them by numbers. That's not a problem. We can also talk about the addition of signals, adding signals. We already talked about this a bit when we talked about this idea of vector addition. Vector addition was naturally element by element. It is consistent with this idea of how we add signals. If I have a signal x of t and I add to it another signal, call it y of t, right? I just element by element add those two pieces together. I'm going to just demonstrate this very quickly in a graphical sense. Let's say here that I had my x of t. My x of t was again a DC signal of 1. So there it is as a function of time. X of t is just this nice DC signal. And then I have another signal. I'm going to go ahead and let this other signal be called y of t, and I'm just going to let it be a sinusoid, something like that. So it's a function of time, and it sits there and toggles between -1 and 1. If I do x of t plus y of t, right, very simple in this case, every different value of time, I just add the corresponding values of x and y. So what do I get? I get a DC offset sinusoid in this case. So this guy is going to sit there and oscillate in a sinusoid way about a DC value of 1. And so it's going to have a peak value of 2 and a minimum value of 0, something like that. Really no surprises here. Everybody has seen this sort of stuff. I'm going to just mention a couple other examples of operations on the dependent variable. And again, I think they're all stuff that you've seen before. We can talk about signal multiplication, right? Signal multiplication, something like x1 of t times x2 of t. How do I interpret that? This is an element by element multiply between signal x1 and signal x2. Each corresponding value of these two signals, x1 and x2 at different times, are multiplied together to create a new signal that is a function of time. So I could call this whole thing another signal, y of t, something along those lines. This multiply here is a multiplication of the dependent, the x's, the signal variable. They have really not much to do with the time variable. Other examples that you might not have really recognized as being operations on the dependent variable might be things like differentiation, right? Differentiation. differentiation. If I look at differentiation, I could do something like this. Y of t equals d dt, right, of x of t. d dt operates on the dependent variable x for all different values of time, right? It just tells us the slope of the waveform. Again, an operation on the dependent variable. If differentiation is one, so is integration. So integration is also an example of an operation on the dependent variable. So I can have something like an integral minus infinity to t of my signal x. Let's make it of a dummy variable of integration tau. So I'm going to call that x of tau d tau, something along those lines. So a running sum, a running integral, right, of that signal. Operations on the dependent variable. It's just all the area from minus infinity up to the current point creates a new value of the amplitude. Most people intrinsically have comfort with operations on the dependent variable. Okay, if there's operations on the dependent variable, there's certainly also operations on the independent variable. So let's talk operations on the independent variable. This is on the t, right? The independent variable. So we'll usually take this as being t, something along those lines, operations on the independent variable. For whatever reason, this always seems to be a little less familiar with most people, so we're going to spend a little bit of time on this. What I think I will do to try to introduce this is I'm going to start out with a question, and so I'm going to give a signal. I'm going to talk about an operation that involves operations on the independent variable, the t variable. I'm going to give a couple of options, and then I'm going to ask you what you think is the correct way of interpreting the expression. So let's start with a question. I'm going to go ahead and start out with a question. To start this question, I'm going to begin by defining a signal x of t. So I'm going to do this graphically for right now. I'm going to go ahead and draw my axis in here. I'm going to let this signal start at -1. And it's going to hold a constant value. I'll just make it a value of 1 up through time t1, and then it's just going to return back down to 0, and it was 0 beforehand. So this is going to be my x of t as a function of t, something along those lines. So I have this nice unit amplitude to duration pulse centered at t equaling 0. Right? So that x of t I'm going to use, and I'm going to create a new signal y of t. I'm going to let y of t be equal to x of 2t plus 3. And what I would like to do is I'd like to give a couple of different options of what that y of t might look like. So one of these options, I'm going to call this guy option A, and then I'm going to give another option later, and I'm going to call that guy option B. What am I going to have option A be? Well, let's go ahead and draw this out for just a minute. I'm going to go ahead and put my axis in here, and I'm going to have a -1, a -2, and a -3, and I'm going to put a little pulse here at -3, going from -3.5 to -2.5 with height 1, right? And I'm going to put a question mark. Is y of t equaling x of 2t plus 3 equal to that guy, or is it equal to maybe this other one? So let's go ahead and put out this other one. I'm going to do the same sort of a labeling on the axis. So -1, -2, -3, something along those lines. This one I'm just going to let the pulse go. Let's make it from -2 to -1, something like that. So still height 1 going from -2 to -1. And I'm going to give those as the two options. I suppose there's other options, but let's just make this a 50-50 game. One of these two guys is right, and if one of them's right, then one of them is also wrong. Here's what I'd like you to do. I'd like you to take a few minutes and think about which of these two waveforms, A or B, is the correct representation of y of t equaling x of 2t plus 3. Just to maybe get you started on this a little bit, let's look at that 2t idea, right? Let's put this in terms of something you have seen before, right? Think of something like cosine of t, right? That's some sort of waveform. It's some sort of sinusoid. If I do cosine of 2t, we all know what that looks like, right? That's a cosine of twice the frequency, so it should oscillate twice as fast, something like that. So when I multiply t by a number that's greater than 1, right, it's like increasing the frequency. It's like scrunching everything together. It's a compression. It should make things operate faster over shorter intervals of time. And it should do so in this case by a factor of 2. If I look at my original signal had width 2, and I'm going to make it operate faster by a factor of 2. That should compress it by a factor of 2. the result should be something that has width 1. Well, if I look at my two results that I've given in here, this one's got a width 1 and this one's got a width 1. So both of them conform to that particular idea. So I don't know if that fully helped us understand which of those two is right, but we at least begin to see something about why one characteristic of these two plots is reasonable given the overall expression here, y of t equaling x of 2t plus 3. So take a minute and think, which one do you believe is the correct representation of y of t equaling x of 2t plus 3, A or B? Hopefully you've come up with something. What I can tell you is that when I give this problem, and I do this in class almost every semester, I've probably done it in class for the past 20 years, what I can tell you is I get about 80% plus of the class telling me that A would be the correct representation of y of t equaling x of 2t plus 3, and I maybe get something like B being 20%. Even if we look no further than this, there would be something a little bit unhappy about this, just because we don't have 100% uniformity from everybody saying what this relatively simple operation is. Probably more surprising to many people is the fact that this A is actually not correct and it is the B that is correct. And so oftentimes people's intuition on this drives them wrong or sends them down the wrong path. 80% of the class oftentimes picks the wrong one in this way, which is why I like and continue, even 20 years into it, giving this particular example. I think sometimes our intuitions are wrong. Intuition can be a really positive thing. It can be a really good driver, but when you've got a wire crossed or something's not being fully checked in there, it can definitely send you down the wrong path as well. So what we would like to do is we'd like to maybe be more methodical in our understanding of operations on the independent variable, and then see if we can return to this and solve this mystery and do it in a way that we don't get confused. The book does a lot of kind of rule memorization in this. I'm going to take a slightly different approach. I'm going to try to take something that just focuses on understanding in a fundamental way what is a function. So let's do a little aside here. So first, I'm just going to say, let's recall what a function is. What a function is. If you remember, you think about what we're doing here. We're doing operations on the independent variable. By saying we're doing operations on the independent variable, we are implying that we are operating on the inside of a function, right? So functions are also implicitly involved here. If I'm operating on the independent variable, right, there is a dependent variable out there somewhere, and that dependent variable is described through this idea of a function. So what is a function? A function is and I'm gonna emphasize this next one. It is a fixed mapping rule, right? And what does it map? It maps the independent variable to the dependent variable. And what we say here is independent variable could be a little bit too restrictive. It's an independent variable, or it could be some expression, involving an independent variable. Whatever it is, that's the argument of my function, is what is going to get mapped to this dependent variable. So it's a fixed mapping rule. So let's actually get rid of all of this. We usually think of it as an independent variable, but we could put an expression in there. So let's say the argument. It maps the argument of the function, right? It's the argument of the function, and it maps it to the dependent value. Let's demonstrate this idea. It seems a little maybe obvious, but let's make sure that we all got it through this example. So I'm going to look at an example that's really simple, and it's a function we need to know anyway. So I'm going to introduce this thing called the unit step function. We're going to call this guy u of t. U of t, by definition in this book, is 0 for t less than 0, and it's 1 for t greater than or equal to 0. This is a light switch function. At t equaling 0, we turn on the light, right? So the function becomes 1. Before that, it was 0. If I was going to plot this guy out, it looks something like this, right? I have different values of time. When t is 1, when it's less than 0, it is going to just be down there at 0. And when I hit at 0, it's going to pop up to 1 and stay 1 forever. So it's an indicator function. It's a light switch function, however you want to view it. It's got two values possible, 0 and 1, and it depends on the argument. Okay, so that would be a typical way of describing this unit step function. As a function, right, it is a fixed mapping rule. It maps that argument. What is the argument in this case? The argument is t. It maps that argument t to some dependent values, in this case 0 or 1, depending on what the values of that argument, in this case t, are. So let's look at this. Let's cast it slightly different. Let's relook at this mapping function, right, or this function u, this unit step function. But instead of saying t, I'm going to do it in a more abstract way. I'm just going to say t of dot. What is t of dot? T of dot is 0 or 1. Why do I say that? Because a function is a fixed mapping rule. The unit step function says you can be 0 or you can be 1. That's all you can be. The fixed part of this is that idea of it being fixed in its output, its dependent variable is 0 or 1. That is fixed. And it's fixed that whenever the argument is 0, I'm going to be outputting a 0. And whenever the argument is greater than or equal to 0, I'm going to be outputting a 1. I think this highlights in a better way what a function is. A function is a fixed mapping rule that takes an argument, whatever the argument it is, and it maps it in a very fixed and predictable way, a way that doesn't change, to the output, the dependent variable output, something along those lines. So now, if I do something like a time shift operation, I think we can understand those operations better using this idea of a fixed mapping rule. So let's go ahead and start with time shift. So let's look at a time shift operation. Time shift operation looks something like this. I'm going to create a new signal y of t, and I'm going to say it's equal to a starting signal x of t minus some fixed amount cap t, right? Now, what will the book do? The book is going to say something like this. It says if t is greater than 0, then we shift right. So they give you some rules. And if t is less than 0, we shift left. So you have to remember these rules. I don't know why we need to memorize these rules. I don't think we have to. I think we can do this just by understanding what a function is. Let's look at a particular example in terms of that unit step. Let's create a new signal y of t as being equal to my unit step, right, of t minus 1. If I used the book expression or the book kind of method, I would see here that my cap t is equal to 1 because 1 is greater than 0. It means shift to the right. Shift to the right by 1, this input function u. So I should be getting something like what? I'm going to come over here 1 unit, and I should be getting something that is holding out at 1 after 1, and it was 0 beforehand, something along those lines. So that should be my y of t as a function of t. So you could try to memorize that, and there's nothing wrong with that. But we could also just look at this in terms of what is that mapping function u. U is, it's either 0 or 1. And when is it 0? It's 0 when its argument, what is its argument? T minus 1 is less than 0. Or when its argument, T minus 1 is greater than equal to 0. I can write this in a little bit more formal way. I can do this, I can do this or a little more simplified way. It's still 0 or 1. I can take this minus 1 on both of these sides and add 1 to either side of those inequalities, and I'm going to get for t less than 1 and for t greater than equal to 1. And I think this, right, is pretty obviously that. So yes, you can memorize the rules. You know, if you have a independent variable minus a constant and the constant is positive, it means shift to the right. Or we can just remember that functions are fixed mapping rules, right? And we can put those modified arguments into the mapping function itself and track points of interest. For example, that edge in this case. Okay, let's look at a different operation. This will be the time scale operation. So time scale operation. We had already hinted at this during our previous example that involved that question that we started this part out with. And so a time scale looks something like this. Y of t equals x of a times t. So I'm multiplying the independent variable now, right, by a factor a. Now the book will say something like this. If the magnitude of a is greater than 1, then we compress x about the origin, right? And if magnitude a is less than 1, then we expand. x about the origin, something along those lines. We'd already gotten some idea of this, like if I had a cosine of t as an example, if I had a, let's get this back up. Every once in a while, these things like to freak out just a little bit. There we go. Bring this back up. X of t, cosine of t, something like that. If I go ahead and I plot this guy out, right, I'm going to get something that looks like a sinusoid. And the first time it comes in here is going to be at t equaling 2 pi. And then it just sits there and it keeps repeating and it keeps repeating before that. If I looked at cosine of 2t, that would be doubling the frequency. That cuts the period in half, right? Now this guy is going to sit there and go twice over 2 pi, and it's going to hit the first peak right there at pi, something like that. So everything got compressed towards the origin by a factor of 2 in this particular case. Again, we could absolutely do this by following the function itself as a fixed mapping rule. So as an example in here, what do I know about cosine? I know that cosine, when its argument, when t equals 2 pi, right, I get that first peak back up there. So when this guy's argument, 2t equals 2 pi, or t equaling pi, and that's exactly what I get. I get that peak moving in by a factor of 2, now to t equaling pi, because I had that multiplicative factor out there before of 2. So we can just track, points of interest or convenient points and absolutely see what these guys are doing. So we've looked at 2 operations, both of which I think aren't hugely surprising. I'm sure you've seen some of these. Just when we start getting some of these guys combined together that oftentimes I think we can make mistakes. Before we do the combined operations, let's talk one more. Let's talk about time inversion or reflection. So we could look at time inversion or reflection as another idea. So if I do something like this, if I say y of t equals x of minus t, I just reflect x, right? This whole thing means reflect x about the origin, reflect x about t equaling 0. So as an example of this, let's go ahead and look at our old friend, the unit step. If I take y of t equals u of minus t, so I'm putting in here the independent variable t is getting replaced with minus t, something along those lines, or multiplied by a negative 1. If I wanted to do this, an easy way is to, again, look at that mapping rule. What is it? It's 0 or 1. It's 0 when what? The argument, and the argument in this case is minus t, is less than 0, and it's 1 when minus t is greater than equal to 0. If I clean that up just a little bit, 0 and 1, I know inequalities when I divide, right, by a negative number on both sides, so I could just get t by itself. Whenever you divide by a negative number in an inequality, that switches the sign or the direction of the inequality. So if I divide minus 1 on both sides, minus t divided by 1 is just t, 0 divided by minus 1 is just 0. I'm going to get t, right, going to be greater than 0, and the other one's going to be t less than equal to 0. If I go ahead and plot that guy out, what do I get? For greater than 0, I get 0, and for 0 and less, I get a value of 1. So this is my y of t as a function of t. And it's exactly as we would have expected. The unit step now has been reflected. It's a turn-off function now, right? So it was on for all time until we hit 0, and then the system turned off, or the signal turned off. Okay, so let's talk combined operations. Combined operations, something like that. So you can have something like this: y of t equals x of a t plus b, right? What do we know is involved in there? Because I'm multiplying t by a, right? That should be a compression, compress, or expand type operation, right? That's the time scale. And because I've got the plus b, that should be like a shift operation. So I can see that both time scaling, that compression or expansion, and shifting are involved here. The problem is, which one do you do first, right? Do you shift and then compress or expand? Or do you compress or expand and then shift? Let's go back up here and take a look at what we had as our original kind of question, right? We had this original signal. I'm going to start just doing everything in blue, right? And I want to think about taking this guy and compressing first. So I'm going to compress. I'm going to compress that guy. What does that do? That makes it like this. It's going to go from minus a half to a half. And then if I shift it, right, what does it do? It's going to come over here at -3 and being that fully one width unit function. So this A part that we looked at, right, it did the compress first, it did the compress, and then it did the shift. Okay, so that's one way of looking at that operation. Turns out it's not right, but that's one way of doing it. How about if I did it the other way first? What if I'd shifted it first? If I had shifted this guy first, right? And so I'm going to do a little bit of erasing here. I'm just going to get these guys out of there. And I'm going to go ahead and think about the shift first. Actually, I can recopy this other one, maybe do it up before. So we had what? We had compress, right? And then we had shift. So the compress did something like this, -1/2 to 1/2, and then we shifted that guy, and it was at -3. Now in this other one, we're going to do a shift first, right? And so what does that do for me? I'm going to come out here at -3, but it was a two-width function there, so it's going to go -4 and -2. And now I'm going to compress this. I compress it about the origin. Everything gets squeezed toward the origin by a factor of 2. So -4 divided by 2 is going to go to -2. So that's at -2. -2 is going to go to -1, something like that. Well, that is this case. That one was this case. We just did two different order of operation here. They both can't be right. There only can be one right. And if we go back to our basic understanding of what is a function, I think we will be good to go. Well, let's do that after I say what the book says. The book talks something about a precedence rule, right? Precedence rule. And the precedence rule goes something like this, that we shift, then scale. So shifting has precedence over scaling. That's another rule to remember. I'm bad at remembering rules. I just don't want to. I don't want to stuff my brain full of a bunch of rules if I can get to them in a different way. So let's look back at this problem instead in terms of functions and just see if we can use what we know about functions. Here is a function x of t. And it is going from -1 to 1, right? Height 1 as a function of t. So let's write out a definition of x of t. X of t equals 1, right? When -1 is less than t is less than 1 and it's 0 otherwise, something like that. We had in this particular problem come up with a new signal y of t. Y of t was equal to x of 2t plus 3. Now we can go through the precedence rule, we can go through a bunch of other stuff, but why do that? Because y of t is just equal to x of t. So it's the same mapping rule. It's a 1 or a 0. It's just the argument has changed now. So it's 1 when what? When -1 is less than 2t plus 3 is less than 1 and it's 0 otherwise. Let's work with that expression right there for when this thing is going to be 1, right? How do I handle or how do I simplify that expression? -1 less than 2t plus 3 less than 1. How do I simplify that? If I want t all by itself, right, the first thing I'm going to do is I'm going to get rid of that 3, right? So this tells me kind of more in an intrinsic way, a kind of obvious way what the precedence has to be. So I'm going to add -3 to everything in this expression. So I'm going to add in -3 to all sides on that. So -1 minus 3 is -4. 2t plus 3 minus 3 is just going to be 2t, and 1 minus 3 is going to be -2. This is a completely identical equivalent expression. I should say equivalent expression. Now what do I want to do? I want to divide everything by 2, right? So now if I divide everything by 2, so I'm going to come in here and I'm going to divide by 2, and I'm going to get -2, because -4 divided by 2 is 2. And I'm going to get less than t less than -2 divided by 2 is just that -1. So I'm going to get it going from -2 to -1, and now I'm ready to go. What do I know? I know that my y of t is equal to 1 or 0, and 1, we have it for a simplified expression now, -2 less than t less than -1, and it's 0 otherwise. And that's exactly what we had plotted in B on this, right? We come over here, -1, -2, -3, so -2 to -1. I just had that height 1. This is my y of t. That is the right answer. I can get it by memorizing a bunch of rules. I also can get it just by tracking, convenient points and remembering that functions are fixed mapping rules where you take the argument, whatever it is, and you map things according to a fixed set of rules. We can't change the rule, we can change the argument, something along those lines. Okay, so let's look at just one other one and see if we can do it as well. Let's create a new function, z of t, and let's again base it on that x of t, but now I'm going to do x of, and I'm going to have this as being minus t by 3, right, plus 1, something along those lines. What do we expect to be going on in here? Because of the minus sign, I expect some sort of reflection to be going on, right? So I see something like, let's actually make that guy a different color. So we see something like this. There's a reflect kind of stuff going in there, right? We see that plus, there should be some shift going on in there. And then I have that divide by 3. That should be an expansion of some sort going on in there. So I've got 3 things going on in this one, right? There's reflection, shift, and expansion. And again, you'd have to go through all the rules in the book, and they kind of get modified when you have that reflection in place. And my statement is, why worry about that? What do I know about x? If I go ahead and plot out x, we've done this a lot of times now, I'm going to have something of 1 minus 1 to 1, right? So I know x of t is equal to 0 or 1, and it's 0 when minus 1 is less than t less than 1, and it's 0 or 1. Oops, I got those backwards, didn't I? So let's get that cleaned up. It is, let's do it like this. It is 1 when minus 1 is less than t less than 1, and it's 0 otherwise. I wonder if I got that wrong otherwise. Nope, I think I got it right. That's good. Okay, and so what was my z now? Z of t is just x, so it's going to be a 1 or a 0. But now it is a 1 when minus 1 is less than whatever the argument was. In this case, minus t by 3 plus 1 less than 1, right? And it's 0 otherwise. Let's deal, right, with that expression so that we can find out where the 2 edges are, right? If we look at the edges of that inequality, we'll be able to tell where the edges of my resulting function z are. So I'm going to add minus 1 to both sides. So I'm going to get minus 2 less than minus t by 3, right? Less than 0, something like that. Multiply everything by 3. That's going to be minus 6 less than minus t less than 0. Now divide by minus 1, right? Dividing by minus 1 is going to change all the inequalities. So that's going to be 6, and now it's going to go the other way, t, right, the other way, and 0. And we could just clean that up in the more standard way, 0 less than t less than 6. So now I know what? I know my z of t is equal to 1 when 0 is less than t is less than 6, and it's 0 otherwise. Go ahead and plot that guy out. And we're going to have 1, 2, 3, 4, 5, 6. So I've got this guy 6. We're going to stay 1 for that set of 6 units. 0 outside of that as a function of time, height 1. What happened in this guy? Well, it definitely got shifted because it's no longer centered at the origin. It definitely got stretched out by a factor of 3. It was a 2 duration signal before. Now it's a 6 duration signal, right? And it turns out there was a reflection as well. If I went back to my original one and I looked at this leftmost edge here at the minus 1 point, we would find that that goes over here to the 6 point. This particular signal being symmetric about its midpoint, you don't really see that reflection, but the reflection is going on. Hopefully with this discussion, you'll be able to really handle any of the basic operations on the independent variable. This is a pretty good place to stop. Next time, we're going to talk more signal classifications. We're going to talk continuous time and discrete time, digital and analog, periodic and aperiodic, as well as some other ones, and go from there.